This lecture demo will cover electrical energy and heat energy and a few sample problems under this topic. Electrical energy in symbol is capital W is equals to the power times time. It can be expressed in three other forms by replacing power in terms of current and resistance, voltage and current and voltage and resistance. The power in this formula is in watts and the time is in seconds. Current must be in amperes, voltage must be in volts, and resistance must be in ohms. While heat energy is represented by a capital letter Q, and heat energy as applied in this topic is actually uh, application is its application is on the heating of water. So the topic of heat energy is very particular on heating of water. That is why the Q here is the heat absorbed of water itself. So by the formula, the heat absorbed of the medium, which is water, is equals to the m Cp delta T. M is the mass of the medium, and then Cp is a specific heat of water, and then delta T is the change in temperature, lower temperature to higher temperature, since this is about heating of water. For water, the specific heat is equals to 1 calorie per gram degree Celsius. This means that a 1 degree Celsius increase in temperature for a 1 gram of water needs 1 calorie energy, or it can also be expressed in terms of kilocalorie if mass is in kilograms. In joules units of energy, we can use the equivalent value of 4.187 for 1 calorie, 4.187 joules for 1 calorie, and this is per gram degree Celsius, or in terms of kilogram mass, it would be in kilojoules. Efficiency of heating is output energy over input energy. The input energy or efficiency of heating is the electrical energy, and the output is the heat absorbed of water. So the input is the electrical energy. To write this equation involving efficiency, energy out and energy in, we can write this in another form, which is the energy in times the efficiency in this is in decimal, that is percent and percent. We shall cancel out the percent, and this is equals to the energy out, wherein the energy out is equals to the mass Cp and delta temperature. In this case, if your efficiency is 100% or 1, then it would simply energy out is also the energy in. For our first example, given here is 2 liters of water with initial temperature of 28 degrees Celsius, and it is required to increase the temperature to boiling point with an heater efficiency of 85%, and the energy rate of electricity is 10 peso per kilowatt, 10 peso per kilowatt hour. Required here is the resistance of the heating element, and the cost of heating, and the time, the time for the 2 liters of water to boil, how long it will take. So say this is our heater. So our energy input is electricity, and energy output is the heat absorbed by the water. We can write here that the energy in is out over the efficiency, or the energy out is the MCP delta T, and we can determine the mass M given the volume of the water, 2 liters. The mass density of water is 1000 kilogram per cubic meter, and 1 cubic meter is 1000 liters, or this is simply 1 kilogram of water per liter, and therefore the mass of water is 2 kilograms. We can use this conversion of or this mass density of water na which is 1 kilogram per liter. Then, knowing the mass, knowing the mass, we use a CP, which is 4.187 kilojoules per kilogram degree Celsius. We choose the CP in joules because we need a unit in watts, and the unit watts is equals to joules per second. So it is important that your CP is aligned to the unknown, or to the unit of the unknown value, so that it would be more simpler to convert the units into the unknown value. So the temperature change, the delta T, is 100 minus 28 degrees. So multiplying these values, the heat absorbed of water is 602.93 kilojoules. This heat absorbed is the output, and therefore dividing this with the efficiency, which is 0.85 in decimal form, this will give us an output or input, an input energy. This is electrical. This is the electrical energy to be used to heat the 2 liters of water and bring it to 100 degrees Celsius. Now, the kilojoules is actually kilowatt seconds. So we convert the kilojoules into kilowatt seconds, and then we have to convert the seconds into hours to make the unit in kilowatt hour. So our input energy is now in kilowatt hour, and needs a 0.197 kilowatt hour energy, electrical energy input, to boil the 2 liters of water. Given the cost of 10 pesos per kilowatt hour, we can now multiply this with the electricity needed, and the cost of heating 2 liters of water is 1.97 pesos. Now for the resistance, since we are given with power and voltage, we can use the equation for resistance involving voltage and power. Or the formula, power is B square over R. So we can now substitute the values and solve for the resistance, and this is 60.5 ohm. Now to determine the time needed for the water to boil, we can use the formula energy power times time. The energy used in the heater times the is equals to the power, or the rated power of the heater, times time. And since the rating of the heater is given, which is 0.8 kilowatt, and the energy, electrical energy use is a 0.197 kilowatt hour, but instead of using the kilowatt hour, it would be better to use the kilowatt seconds. So in kilowatt seconds, it is 709.33 divided by the power, which is 0.8 kilowatt. It is equals to 886.66 seconds, or in minutes, divide this by 60 minutes or 60 seconds. In minutes, it will take about 14.78 minutes for the water to boil. In the next example, a water heater rated 1.5 kilowatt was used in a shower. The water flows into the heater at a rate of 50 cubic centimeter per second at a temperature of 18 degrees Celsius. Find the outlet temperature of the water heater if the heater has a heat loss of 5%. So we have here a heater, water heater, and a water of this is a mass flow rate 50 cubic centimeter per second enters into the heater and leaves at the other side at the same rate. So it is not mentioned that it leaves at a different rate, so we shall assume that it leaves at the same rate. The initial temperature is 18 degrees. Now the final temperature is unknown. The heater is rated 1.5 kilowatts. In this problem, with the formula of 0.95 energy in is equals to mass Cp, and then the delta temperature. We can see that in this equation, we have only a mass and not a mass flow rate. In this equation, time is not reflected, but we know that the 0.95 energy is actually power in. The energy in is power in times time, mass Cp delta time, or the delta time may be represented as T2, the final temperature, minus T1, the initial temperature. I will transfer the temperature at the right side, making the equation 0.95 times the power in. This is the input power to the heater, which is the rating of the uh, water heater, and the mass is to be divided with time, Cp, T2 minus T1. Then you can see that the mass over time appears in the equation, which is can be determined through the volume flow rate. So we need to determine the mass flow rate that enters into the heater through the volume of 50 cubic centimeter per second. From the mass density of 1 gram per cubic centimeter, we can now determine the mass flow rate. So 0.95, the power input is 1.5 kilowatts. So this is times 10 to the 3. And mass is shall be derived from the volume, 50 cubic centimeter. This is per seconds, to be multiplied with 1 gram per cubic centimeter, which is mass density of water. Multiplied with the Cp, which is 4.187. This is joules per gram Celsius. Times the change in temperature, which is the final temperature minus the initial temperature 18 degrees. You can see that in this equation, this is power in watts, which is actually joules per seconds. The cubic centimeter will cancel out. What remains here is gram. The gram and gram will cancel out. the degrees Celsius will cancel out. What remains here is the joules and seconds, and on the other side it is also joules seconds. And so therefore we can now calculate the final temperature or the outlet temperature of the heater. And this gives us 24.8 degrees Celsius. There is an increase of 6 degrees, 6.8 degrees Celsius due to the 1.5 kilowatt heater at a volume flow rate of 50 cubic centimeter per second. Now, the 6.8 degrees Celsius may change depending on the flow, the volume of water that passes through the heater.